Okay, thank you. Thanks for coming to the session. I am Pushkar Khadilkar and I am accompanied by my colleague Vaibhav Jain. We are both members of LOIDB engineering team, and in today's session, we'll show you how you can use LOIDB to power AI-driven applications. First, we'll give you a quick overview of LOIDB and its unique capabilities. Next, we'll break down the fundamentals of vector embeddings and why they are crucial for AI applications. And then we'll dive into the heart of it on how LRDB AI makes working with vectors seamless within your workflow. So alloys are made by melting and fusing elements together to make something new with grade workload you can throw at it. And full PostgreSQL compatibility means you regain the freedom to run your application benefiting from the entire Postgres ecosystem. So LIDB really is the next generation database built for the future. It is optimized for building enterprise Gen AI apps which require accurate and relevant data. It offers best-in-class performance for transactional, analytical, and vector queries. We'll dive more into the offers a new level of reliability and availability. We offer 4 nines of availability that includes not only unplanned failover, but also database maintenance. LOIDB can detect automatically and recover from most database errors within 60 seconds. And it can do that independent of the database load or size. So that means recovery is fast and predictable for any data size. Our architecture also supports online instance resizing and database maintenance. So the LOIDB primary node can restart the normal operations in seconds, and the read pool node can take advantage of the read pool for writes. We support up to 128 vCPUs. LOIDB also includes autopilot capabilities to handle automatic vacuum management, memory management, so that the probability of these errors happening is reduced. And we have embedded AI and email capabilities for features like Index Advisor, where it can learn from your workload and then automatically recommend indexes that are best suited for that workload. We also have an integration with Vertex AI, which is Google Cloud service for hosting models. And we'll go into more details of this since it's related to this session. For analytical performance, LOIDB offers a columnar engine which stores data in columnar format for fast analytical queries. And we also support auto-columnarization so that database can automatically move data in and out of columnar engine based on your workload. LOIDB Omni is a high performance downloadable version of LOIDB. It meets customers where they are. You can run LOIDB Omni anywhere, on premise, in any cloud, at the edge, or even on developer laptops. It includes best of LOIDB features like automatic management, columnar engine, Vertex AI integration for running model inferencing within database. And that way you have 2 options offered. One is the LOIDB cloud service in GCP, and the other is Omni, which you can run anywhere. And the topic we are presenting today, that works the same way on both LOIDB and LOIDB Omni. So now let's dive into the details of vector embeddings. So vector embeddings are a powerful way to transform your unstructured data into formats that machines can understand well. So vector is a mathematical object that has direction and magnitude, and we can represent any type of data such as videos, text, images as vectors, and that's what we call as vector embedding. And general idea is that the vector embedding encodes the semantic meaning of the input data. So the semantically similar items have vector embeddings that are closer together. So let's take an example here. So let's suppose we have a corpus of articles which are talking about movies, actors, and music. And example shows embeddings for 2 articles. So let's say the embeddings can represent how much percentage of that article is talking about each topic. So the first article is talking 10% about actors, 2% about music, and 30% about movies. So if we are searching for something related to music, this won't be the relevant article. And this is just a toy example. In reality, the embeddings have hundreds of dimensions. From PostgreSQL perspective, we can think of embedding as an array of floating point numbers. So that is embedding. Now let's see how we can utilize the embeddings to unlock the value hidden within your unstructured data. So the process starts with the input, which can be images, videos, news articles, anything. We feed this data into a deep neural network that is trained to transform input data into meaningful vector embeddings. And so the model ensures that the related items have embeddings clustered together. And so this way we effectively transform the unstructured data into a fixed dimensional vector that is much easier to work with, and that also encodes the semantic meaning. So this way the vector embeddings make the semantic search possible by just doing the vector comparison. And like normal databases, doing vector comparison for your entire input data set is expensive. So we require a special type of index, that is where the approximate nearest neighbor index and search comes in. And with that we can efficiently retrieve the data without looking at the entire input data set. So that's the vector embedding. Now we'll show how AlloyDB is useful in the Gen AI app context. So no discussion of Gen AI app is complete without LLMs. So LLMs have recently done a lot of innovations in the generative AI area, and they have a tremendous capability to generate human-like text, translate languages, and even generate new creative content. They are trained on vast amount of publicly available data. The two main pieces of information LLM uses are the training data on which it was trained and the user prompt. So when you are talking with chatbot or something, so it has the information user provided in the prompt and its training data set, but it doesn't have a direct access to the business data or the latest information. And such information is required for enterprise Gen AI apps so that the response returned is accurate, correct, and reflects the latest state of the world. So to solve this problem, a hybrid AI technique called retrieval augmented generation is used. So in this process, in the retrieval, we retrieve the latest information from an external data source, and then we provide that as an additional context to the LLM. So now LLMs have three things to work with: their input training data set, the user prompt, and the additional context. And that way LLMs can combine this information to generate factually correct, consistent output required for the application. And that is where the databases come in. So the talk, why do we require this in the databases? So databases have your latest up-to-date information, and this information can help LLMs to ground them for accuracy and relevance. And the idea is that the most of the data being used in these applications is unstructured. So the vector embeddings which we discussed earlier help us in converting that into a format that databases can work with, and the vector indexes are then used within database to efficiently search them. And the best part is that you can already do this where your data already lives. So you already have your database which is part of a robust ecosystem which has the critical business, performance, reliability requirements that you require. And developers are already familiar with the database. So if we can do this within the database, then we can offer a very powerful and simple way for developers to build Gen AI apps. In the next session, we'll talk about AlloyDB AI and how AlloyDB AI helps in solving this problem. So AlloyDB AI is a collection of capabilities that include embedding generation. So we can generate embeddings directly within the database using the familiar PostgreSQL syntax. So we don't have to leave the database or build any application code to generate embeddings. It also has the storage, querying, and indexing capabilities with some improvements for performance. And it integrates with the other rest of the open source ecosystem like LangChain. And we are excited to announce that since yesterday, AlloyDB AI is now generally available. So this is a sample architecture of just to get an idea of how databases and LLMs can work together. So in this example, we have some unstructured data which is used by the Gen AI app. As a pre-processing, we have to generate embeddings for them, and that we can do using an embedding models, and we can store the embeddings in the database. Next, when the Gen AI app gets a query from user, so suppose let's say user has purchased some product and they are not satisfied with product and they want to return that product, and they give a query like, I have purchased this particular product, when can I return it? So LLMs can generate a proper English well formatted information, but the information about what is your return policy, the latest information for that is available in the database. So in this setup, LLM apps can convert the input query into embedding using the model. They can send that information to AlloyDB to do a semantic search to find this within the database on what is the policy, return policy, and value returned by AlloyDB is provided as additional context to the LLM. So now LLM has user's original query information that this particular product has 60 days return policy, and that way it can construct the response which is accurate with the latest available information. Vaibhav will walk through exactly how AlloyDB helps us with the particular features required here.
All right, thanks Pushkar. So hey, I'm Vaibhav, I work in Google. So now we are going to talk about how AlloyDB solves the Gen AI problem. So there are three things that Pushkar talked about. First is we need to create the embeddings. Second, we need to store embeddings. And third is we need to query those embeddings. So we start with the first step here. We allow a SQL syntax to generate embeddings from within the database. And the way we do that is we have created a new extension. It's called Google ML integration. That extension provides two methods. One is ML predict row and the other is embeddings. So the embeddings method integrates directly with the embedding generation models that exist in Google's model garden. So here, if we look at the example, we have the model we are talking about is text embedding gecko, and notice the @001. That's the version number of the model which will be used to generate embeddings. And we are reading all the data from consumer details table to generate embeddings for the entire database. This is not storing it, this is just a read part of it. You can similarly store it by putting it in an update clause or something as well. Same thing goes for ML predict row, but ML predict row is more generic. It allows customers to interact with any model which is hosted in ML model garden of Vertex AIs, and they can also use it to interact with any model which they have hosted on the Vertex AI platform, which is Google's AI ML platform in GCP. So in the first example we see, we are talking to a chat-based model, which is text bison. And here, notice we have not provided the model version. So this means it's going to use the latest version of the model, which is available from Vertex AI. This is all from within the database. You can use, these are all row valued functions. So you can use them in generated columns. You can use them in updated statements. You can use them anywhere a row valued function can be used. And also notice the For the generic ML predict row method, the syntax we have chosen is a generic JSON response format. So the idea is all the models which are hosted on public endpoints support a HTTP-based request response model. And all the general ones use a JSON-based request response model. So that's why we have this in a JSON format. So here we have hand constructed the JSON object like this way. You could also use like PG's helper functions like PG, JSON, whichever one you like. The second part is the requests that we make to these models, they are generally slow. Some of it is because of the network, some of it is because of the models themselves. So we also allow customers to pass in a batch of requests in ML predict row. So you can send a batch of requests and you can get predictions out of those in a batch format. So that helps with the network latency part. The actual time taken by the LLMs is not going to change. That is model dependent. So this helps us generate embeddings. Now comes the second part is we need to store and search embeddings. So PG Vector is an open extension which exists, which allows customers to create vectors, store vectors, and it has two types of indexes right now, HNSW and IVF flat. The syntax is pretty clear here. So this is what I was explaining previously. This is a row valued function and it can be used in an alter table statement, and it can be as a generated column also. Coming to the vector index parts, the syntax, this is from PG Vector. The syntax is very clear. It's similar to what a B-tree syntax is. We have a different index type, IVF flat, and we have some more parameters which are required for the IVF flat index to work. What we have done is we have, since AlloyDB is using best of both worlds, PG and the Google's storage part, we have deeper integration with the storage engine and the query engine, which allows us to get up to 10x more throughput on vector search queries than what PG Vector supports. And these are based on benchmarks that exist. Like there are multiple benchmarks that are available publicly, ANN, big ANN, and we see up to 10x faster vector search queries on those benchmarks. So diving deeper into one of the index, so the interesting thing here is we also have a new index type. It's called IVF. This is a new index type that we added to AlloyDB, and we'll go into the details of that next. So what is an IVF index? Before we discuss that, let's discuss what IVF flat index is. The vectors are stored as is in the index. So a vector, as Pushkar was mentioning, it can have dimensions anywhere from 25 if you're using a swivel index or swivel model, 50 if you're using an LLM, and if you're using a bigger ones, you can have 786, 1500, or even larger if you're using a bigger model. And if we store directly those into the database, we have to pay the storage cost, we have to pay the query cost. So all that gets impacted. And overall, the way query processing works is IVF flat is a tree-based index. Vectors get allocated into clusters. Each cluster has a vector which is close to themselves, and each is represented by a centroid. When a query comes in, depending upon the number of lists that were configured, and that's the number of clusters, customers can query using a probe function, which out of these 20 lists, let's say, how many do you actually want to probe to get the closest vectors out of it? So this works well, but in case of large data sets, the data that you're storing can get very large. So what we do is this is also a research topic, by the way, vector search. There is a lot of research that has happened in open public forum regarding this. So this is one of the techniques that is available publicly as well, which is called a scalar quantization technique, specifically this. So what this technique does is it converts floating point numbers into a smaller data type. In this case, we are converting it from a 4-byte float. Each is a 4-byte float. We convert that into a 1-byte int, and we store that instead of storing the entire vector. So what that allows us to do is it optimizes on the storage part first. Second, since we have less data, query processing improves, and we get better throughput. And because of this, IVF flat can only allow indexing on 2K dimension vectors. Because of this compression and optimization, we can create an index on up to 8K dimension vectors as well. And there are other quantization techniques that exist, but this is the one that we launched. And as Pushkar was mentioning, AlloyDB AI is GA, so this is available for public use. One thing to note here is what I didn't mention is around recall. So the way we measure the performance of indexes is one, how much throughput your queries are providing, and second is what's the recall number. What recall means is what's your return values compared to the actual values that you would have returned. So there are two types of ways we can do a query on an index. One is an absolute neighbor search, and second is approximate neighbor search. So recall is a percentage of what was returned versus what is the actual one, and that's how we measure. So whenever we measure the performance of a vector index, we have to measure both. Now here, when I mentioned the performance improves, because of this quantization technique, generally what happens is there is not enough recall loss that customers will notice, because the recalls that customers generally care about is 97, 98, 99% or so. This one is within that benchmark sort of, and it allows us to have better throughput without having much impact on recall. All right. And the other ones are the HNSW-based algorithms. Those are graph-based algorithms, and that's something new which PG announced recently. There are problems compared with HNSW to IVF/IVF-led indexes. One is HNSW, since it's a graph-based algorithm, the storage requirement for it is larger compared to these index types. Second, the performance is comparable, but building of those indexes takes a really long time compared to these. These are simple tree-based ones, so they get built much faster compared to HNSW indexes. All right. And we have some resources now. Here we have links for AlloyDB, AlloyDB Omni, AlloyDB AI, as Pushkar just announced, is went GA. So there's a link for that. We also have a code lab where it's easy to go through of whatever we just explained, how to generate embeddings, store them, query them, and get them added to your LangChain-based application. There is also a demo, and if you need a live demo, please come to the booth. We'll show you how it actually works on a real cluster. Thank you. So are there any questions? Feel free to ask. Yeah, okay.
Hello. Yeah, why have you chosen Postgres? Like, is it mainly for the existing databases, which existing data of lot of companies are there in Postgres, and they want to deploy LLM on top of that, or just from LLM perspective, Postgres is more powerful compared to any other database technology which is available?
So PG is like a very well-known open source database. Customers going forward, or what customers are generally doing, is they don't want to get into a vendor lock-in problem. And they want to use open source databases, and PG is one of the top choices that customers have when they talk about databases from open source community. So that's why we have AlloyDB. Now the second question is, how do customers build GenAI-based apps on their existing apps, which already use PG? Answer is, we bring vector search to PG, and that allows customers to continue getting the benefit of open source PG database along with GenAI, and that's why we did this.
But for vector-based application search, does it give more advantage compared to any other database technology which is available, right? There are more advanced databases which have been developed. I'm just asking, like, in terms of exploration, when you say mixing that alloy, right, mixing database technology. So was the PG top choice for in terms of performance itself, which it overpassed over others, or it's the default choice because open source and everyone is?
PG is the default choice for open source based databases of customers, and we need to allow customers better functionality on top of whatever already exists and build GenAI apps going forward. So this bridges that gap.
All right, thank you.
So you said you support batching.
Yes.
So I'm guessing what you are doing is taking multiple requests and sending that entire request to the LLM model. But what if the LLM model itself doesn't support multiple requests?
Nothing much we can do. It's a limitation of the model at that point. If the model supports batching, we allow you to do so. If the model supports, let's say some models like the bigger ones only support batches of size 2 or 3. Some support batches of size 100, 500 also. So whatever is supported, we try to use that. If the model doesn't support itself, like not much we can do from our side here.
So you can still run multiple queries in parallel. Let's say batch size limit is 10. So instead of running one query with 10, you have 100, you could run 10 queries in parallel.
But in that case also the endpoint should take multiple concurrent requests, right?
Yeah.
It should be able to take that.
Yeah, usually what we have seen is the limit is, the first hurdle is on the batch size within a single request. Like that's more fundamental limitation. So that has a workaround of running multiple queries.
And generally, all the models which are hosted in public endpoints, they do allow concurrent requests to be processed because it's a multi-tenant endpoint at that point, right? So they need to allow concurrency. There are different limitations on that a single client sort of can only do 10 requests, 100 requests, depends again upon the endpoint to endpoint.
Any other questions?
So, considering coming from the background of OLTP and OLAP databases, and now that we know that if your OLTP database grow very large in size, you should keep them small. You should move them to OLAP database when they grow large, and then when they grow large, you should move to data lakes. So, what is happening currently in the arena of vector databases, when the size of the data that your model is maintaining, or it generates more and more, and it gets bigger and bigger, what comes next after it? And are there any pipelines that are being built or being thought of right now to address that challenge of the growth of size as the data of vector embeddings grow and grow in future?
Okay, so if I understood the question correctly, what happens if the vector data set is huge and PG can't support that well? Okay, so I think there are two parts to that question. First part is, as you said, live data sets are generally smaller and the query patterns only use some of the data set. So that can be served out of the PG database itself. Now, there are other parts of the question, which is how do we use whatever exists for training or updating the model for the incoming data that happened? There are purpose-built services in Vertex AI which help you train and deploy and train the model, verify it, test it, and then only move it to production. So answer the second part of the question, how do we have a pipeline? So GCP supports an ecosystem of services which allow you to do seamless migration from one place to another, which helps you in this journey.
Yeah. And to add, there are already some existing features in LRDB that you can use to solve some of these problems. So as long as your working set fits in the cache, you're good. A lot of these queries are read-only. So we have read pool features which are horizontally scalable. So you could redirect the read pool queries there. And we offer almost limitless storage. It can grow to very large volume. So as long as the workload is such that even if there is a lot of data, if the current working set required fits well within the caches, the LRDB can work well with that. And as you said, like some of these optimizations that we mentioned, like scalar quantization, they also help with the increase in the dimension. So also the scale, but like even for single values, many models are generating even vectors with higher dimensions. So some of these optimizations will also help in compressing that and making sure that we can support them. So we hope that the presentation was useful to you. If you have more questions, we are happy to answer them at the GCP booth and also to show you a demo. Thank you.
Thank you very much.